It's a great honor and privilege to be with you this afternoon. Actually, this is the second Skinner lecture that I've given. Maybe people don't know that or realize it. About 9 years ago, if this works, I gave a talk in Phoenix, Arizona, called The Complementary Nature of Coordination Dynamics, with the great man, of course, in mind, and talked a lot about learning in that presentation. My story today is going to be rather different. And I'm going to start it really with a personal story, which I've never really done in typical lectures. But it allows me to get to where I want to go with you this afternoon. So the personal story begins, as Jack in his very kind introduction said, with a study of motor control, human movement actually, which is a remarkably complex behavior. Complex in the sense that it has very many microscopic components, neurons, 10 to the 14th, neurons and neuronal connections, many muscles, joints, receptors, of course, on the sensory and perceptual side. So it's something we all take for granted, but it nevertheless is a remarkable feat of a complex living system, as it were, living in some sort of lower dimensional place. As I talk to you, as I move my hands around, this is not enormously complex, but underneath, if we were able to look very carefully, we would see that it's probably bewilderingly complex. So I had this idea that somehow the study of human movement could be enhanced if we brought in notions of non-equilibrium physics. A person called Ilya Prigogine had won the Nobel Prize in 1977. I won't go into all the history, but basically it was for an understanding of what he called dissipative structures. And then a person that I eventually ended up and still working with, he's now over 90 years old, Herman Haken, had written this book, Synergetics. Haken is the father of laser theory. So I had this idea that maybe that somehow human movement could be studied in terms of pattern formation in these nonlinear systems. And the second idea I had was that maybe the way horses or ponies change their gaits might be analogous to the way matter changes its state. Ordinary matter changes its state from water from liquid to gas to solid and so on. And then because I was at Yale Haskins Laboratories, which I was studying speech production actually at the time, I couldn't study ponies walking or anything like that. But I had this idea, somehow, I don't know where it came from, probably the yellow pages, nobody remembers possibly the yellow pages of telephone books, of letting your fingers do the walking. And that was sort of a sudden kind of thing to me, that I could now have a little model system where I could actually probe this whole idea that somehow the coordination of behavior was deeply related to other non-equilibrium phase transitions in physical and chemical and biological systems, actually. And this second point, so the emergence of this idea was a kind of phase transition. And then, many years later, actually, the evolutionary biologist cum phenomenologist Maxine Sheets Johnston, in her remarkable writings, in fact, in a book called The Primacy of Movement, which is in the second edition, it's one of the best books on movement and the experience of movement that I've ever read. But Maxine took this little story up. She took it up in a way that says, hey, this is a breakthrough to a new mode of thinking, a different way of thinking. And in fact, thinking as a phenomenologist, It's just as real, this idea, this creation of the idea, or this sort of eureka-like phenomenon, is just as real as gate transitions. And for that matter, one pushed it further, is just as real as physical phase transitions when a system changes its state. So for Maxine, she used these words coordination and constitution, which is a phenomenological term, span the mind and the body. For her, there is no real distinction or incommensurability between first-order descriptions of behavior, as it were, the subjective aspects of behavior, and the third-person, ordinary, objective, scientific descriptions of behavior. For her, they were actually basically one, or at least complementary. So that's really where I want to get to today. It's the first time I've given this talk. I want to get to this place that maybe phase transitions here are a link to the connection between mind, movement, and matter. And actually in my abstract I said the order might be important. So let's start with matter, then go to movement, and then go to mind. And that's basically what I'm going to try to do. I have to move a little bit faster now. So here's the basic idea that there are phase transitions in inanimate matter and animate movement, including the brain. I'll show you some of these. I won't be able to go into a great deal of detail. These phase transitions are prominent features of the self-organizing laws that bind us, these laws that bind us, the coordination dynamics that Jack referred to. And the basic hypothesis here, or the notion on the floor that I'd like you to entertain at 5:10 on a Sunday evening, is maybe these phase transitions constitute the missing link between matter and mind. And by the way, many great scientists, probably when they get old, like I am, come to this issue eventually. So Max Delbruck, lovely stories of Delbruck, you know. He got the Nobel Prize the same year as Samuel Beckett. And Beckett, of course, didn't go to the Nobel Prize ceremony at all. He took the money, but he didn't go to the... And Delbruck, in his writings, said he was really disappointed because he was struck by the impermanence of science and the permanence of literature. Yeah. I can't go on, I'll go on, you know? Attendons Godot, etc. Yeah. Okay. So I want to organize this in terms of this other scientist who's also got a very interesting Irish history, because he wrote this book, What is Life, in Dublin during the Second World War. And it frames the issue for me here, for us this evening, and allows me to move through this, I think, in a good time. So here's Schrödinger's epilogue in What is Life, this famous book that stimulated, or said to stimulate at least, modern molecular biology. I've not really seen this discussed very much. So here it is, you see it. My body functions as a pure mechanism, according to the laws of nature, yet I know by incontrovertible direct experience that I am directing its motions, of which I foresee the effects. Therefore, the only possible inference is that that is to say, every conscious mind that has ever said or felt I, am the person, if any, who controls the motion of the atoms according to the laws of nature. And at the end of this little book, he says, what is this I? And here I want to inquire where this I comes from. If you like, I'm going to show you that the spontaneous formation of patterns of behavior in complex living systems works according to principles and laws of self-organizing systems. So the self-organization actually means there is no self inside the system at all. There's organization, but there's no little program or organizer doing the organizing. And I'll show you one slide just of a paper in Nature last week that makes this mistake. But the idea is that somehow this self-organization gives rise to the experience of self, of I. I direct the motions of my body. All right. So what are the laws of? Well, they're laws of coordination. I put this in as a little place marker for you. I do not see any way to avoid the problem of coordination and still understand the physical basis of life. This is an inspirational quote for me from Howard Patti. And 50 years after What is Life, in Dublin, they had What is Life the next 50 years, and this gentleman and myself, Herman Haken, wrote a paper called New Laws to be Expected in the Organism, because that's what Schrödinger had suggested. Nobody really followed that. After the discovery of the molecular structure of heredity, the DNA molecule, the idea that there would be new laws in the organism was kaput, as it were. So in this particular formalism, what you see here is what are called potential pictures. They are a description of the flow of states as a function of a parameter called a control parameter that simply moves this system. You can see here, can people, is this working? Is it's not showing, okay. So do I have a pointer perhaps? So it's showing here, just for present purposes, I'll show this again slightly differently shortly, but just get into your heads here, there's really two factors here. One is the coupling among the components that produce these coordinated states. The little black balls correspond to coordinated states. And as you change this coupling, the system changes from, for example, having multiple states to just one state. The little balls that are open are unstable states. And here on the y-axis is the other factor. That's to say, let's just call it for the moment diversity or heterogeneity. This simply means that the components are not the same. The HKB model, so that's a model of coordinated behavior, has delta omega. This term is just the top line. But further developments led to this additional picture, which turns out to be much richer. Let me just leave it like that. Get the idea here that there are attractive states of a nonlinear dynamical system, that you can move this system through its different assembly of states, and that the factors that matter are the coupling between the components and the heterogeneity or differences between the components. In a way, that's really life, you know. How you're coupled to your world, coupled to each other, depends on the strength of the coupling, and it depends also on just your individual differences, as it were, how different you are from each other. So, this is sort of a synthetic statement that the laws to be expected in the organism, namely these coordination dynamics ideas, the laws describe the flow of coordination states produced by functional synergies or coordinative structures. So once more with feeling, they describe the flow of coordination states produced by coordinative structures or functional synergies. Okay? So that's the agenda here. What are these coordinative structures? I don't have time to go into all the evidence for that, but one idea is that they're the significant units of biological coordination at all scales. Let me just give you, there's too many words on this slide, but let me just give you the main concept here, that the coordinative structure, in my mind, is the only entity, biologically based entity, that allows for the same outcome to be achieved in many ways using different components and pathways. Jerry Edelman called this degeneracy. We would call it perhaps equifinality in older times. Different outcomes can be achieved using the same components, right? So I can produce speech using my lips and jaw, and I can chew using my lips and jaw. I'm using the same material, but it's organized for particular functions. That's the idea. Function here is number one, right? That's not necessarily the standard notion, by the way. And these are sort of softly assembled. I mean, these are just words here, but there's a lot of nice evidence that shows, for example, that if you perturb one of these coordinative structures in one place, other parts of the system will respond adaptively, even though they're far removed from where you perturb things. We're used to seeing, well, if I perturb my limb here, my limb will respond, right? I'll come back to some equilibrium position. But we're not so used to the idea that if I perturb here, I see the first response being the back of my leg. And that's the nature of these softly assembled coordinative structures. And they're seen at multiple levels. That's a lecture on its own. But the idea is that these softly assembled coordinative structures are units of biological coordination, and that they're governed really by two forces, evolution and self-organization. The evolutionary part I can only give lip service to here. It comes from John Maynard Smith's writings, Smith and Zathmari. Here's the basic idea. There's a rowing example, which is cast in terms of game theory. If cooperative interactions among two or more individuals, related or unrelated, not necessarily of the same kin, produce selectively advantageous synergistic effects for all parties on the average, the cooperating players may become a unit of selection. So the idea here, if you like, is that the synergy here is what's selected. That's a hypothesis at the moment, but there's some very nice evidence for it. So as you can see with the rowers here, you can see when each rower has two paddles or two oars, that's two oars, that if they cooperate very well, they can get to the end of from one part of the stream or the river to another. You can see in the case where each has only one oar, however, that if they don't cooperate, they're going to go around in circles. So that's the key idea. You better cooperate if you're going to produce some functional end. And this is called synergistic selection. And it's seen, I would say, at multiple levels, from the levels of bidirectional coupling between neurons up to the levels of groups of neurons, up to the levels of interacting brains, which is an area that we've been studying considerably. And self-organization, I'm using this quotation from a well-known paper by the Nobel laureate Robert Laughlin and David Pines, who just passed away recently. The most profound revolution in the study of matter in the last 30 years or so was the discovery of emergent physical phenomena regulated by higher-ordered principles. Just a side point. This paper that I show you here, Self-Organization of a Human Organizer by Combined WNT and Nodal Signaling, appeared in Nature this week. And it's about the process of gastrulation of embryonic development. And the point I just want to make is that even though this gastrulation is a process of self-organization, of pattern formation, where you go from just a long strip of epithelial cells, and these cells form layers, the germ layers that we all know about. This is a process of self-organization. Nevertheless, we cannot resist saying, this is the organizer. There's an organizer in here doing this, when in fact the system, when exposed to different substances, produces this structure in a self-organized way. And just as far as matter is concerned, this is Kenneth Wilson. And actually, just last year, there was another Nobel Prize for phase transitions called topological phase transitions, which actually we've seen in coordinated movement time and time again and published on. But the key idea here is that what Wilson is showing you here is a manifold, a description here of the dynamics. And you can see there's sort of two peaks and two sinkholes, and they join together at a saddle point, at this saddle point here. And at this saddle point, it turns out with Wilson's methods that you can actually characterize very different material systems with exactly the same description. Okay? That's a key point. And this is called universality. So the universality of phase transitions as a mechanism of self-organization was demonstrated by Wilson. These systems have very different material properties, but they behave the same near criticality. That's the key idea. Now, just to summarize this whole notion of self-organization, and this is just for really, as it were, the students in the audience. We're all students. But here's a sort of synthesis. In complex open systems, patterns arise spontaneously in a self-organized fashion. That's what it means, the spontaneous formation of pattern. There's no ghost in the machine. There's no organizer, no program. Compositional complexity, very many components, nonlinear interactions. Second key idea is that these emerging patterns are characterized by just a few coordination variables. I call them coordination variables because of the biological and psychological context, but these are equivalent to what physicists call order parameters. These order parameters are quantities that capture the microscopic behavior of the system. They're macroscopic quantities, but they describe the microscopic interactions. The third point is that what parameters do here is they don't prescribe, they don't tell the system what to do. They actually just move this dynamical system through its repertoire of behaviors. That's what they actually do. So these are called control parameters. They lead the system through different patterns but don't prescribe them. At these critical points, this is where you can actually see predicted properties. Loss of stability is the mechanism. Dynamic instability is the mechanism. This leads to the emergence of new patterns and switching between patterns and fluctuations. Variability is a key aspect there, it turns out, in many, many experiments. And then when this system has formed these patterns, the pattern dynamics are now, as it were, simple. They're simple but nonlinear. Simple nonlinear dynamics. They give rise to all the behavioral patterns that can be observed. So they can have complex solutions and so on. So this is a kind of foundation. These points 1 through 5 are something you could grab onto because they've been demonstrated numerous times in physical theory and in multiple experiments. These are, actually this is an old slide, but in many different systems here, I'm not going to go into any of them really, these phase transitions have been observed in coordinated movement, even between people. The typical phenomena that have been seen include critical fluctuations and something called critical slowing down. I'll show you that in a second. This is a slide from my physicist colleague. These laws of coordination are universal. They're universal because they're very, very different systems, but they're all doing very similar things and can be described with the same mathematical description. Whether they involve one brain or two brains, the basic features in this case of rhythmic coordination are, you can see two stable states, two stable modes at low rates of movement, in phase and antiphase. There's a kind of symmetry there. The antiphase loses its stability as you push the system. It loses its stability and you jump into the next available state. So it switches to in phase at a critical rate, and there's no switch from in phase when you start in the in phase mode, and this is really a kind of memory or hysteresis. I'll show you a little bit. So here's the, if I can, show you one little piece of mathematics. I'm going along nicely here. This is called the extended HKB model, and really all you need to really focus on is that this phi variable is the order parameter. It's the relative phase between the components as the system is evolving in time. There's a coupling. There must be a coupling between the components, and that's given by these sign terms. And all biological systems, all systems exhibit fluctuations. So just for now, you can see that the order parameter equation here contains individual diversity or heterogeneity. It contains the coupling that's necessary, and it contains fluctuations that are crucial for taking the system into new places, for exploring the repertoire of states. So just bear with me here. This is this flow of coordination states that I was telling you about. And the way you see this is by looking at phi dot against phi. This is the HKB equation here. And a way to do this is just plot this function and look at where the equilibrium points in the system are. And you can see there's one here close to in phase and one here close to anti-phase. The ones in between, the open dots, are unstable fixed points or repellers. But now as you change the coupling, which is related to parameters that you change in experiments, you actually lose this anti-phase stability. You see it lifts off the line, and all you're left with here is the one near in phase. So here you've gone from a system that has multiple stable patterns of behavior. As it's pushed, it switches, it operates according to these transition principles. And then even further on, you see this regime where there's no longer any stable states at all, this metastable regime, okay? And the interesting thing is that there's still sort of remnants or ghosts of where these fixed points used to be, okay? So there's no longer any stability in the system at all. It's metastable, beyond stability. And to the extent that neuroscientists would call these stable states integrated, they're phase-locked states, you switch among them. This is a regime where there's both a tendency for the system to integrate, to come together, and a tendency for the parts to express their autonomy. See? So it's this struggle between the coordinative, cooperative aspect and the tendency for the components to do their own thing. That's the game that's being played here. So sorry for that little piece of mathematics. Nevertheless, it covers a whole bunch of stuff here. I could use fancy words for this. Fancy words have been used for this description. I won't bother using them here. But this simple mathematical equation characterized symmetry, symmetry breaking, multi-stability, bifurcation, instability, transitions, metastability. It's an emergent higher order rule that seems to cut across different systems, different levels, different processes. And that actually is at the core of this quotation that I gave you earlier from Robert Laughlin and David Pines, that these general rules emerge even though you cannot derive them in an analytic sense from microscopic interactions. You can try pretty damned hard, and you can do it with approximations in some cases. But in general, these are rules at a particular level of organization at this so-called order parameter collective state level. So these deal with collective states. And it's the collective states that have to be identified as behavioral scientists that really is a major aspect of the research program. Now, this is not just movements, but you can take this into the brain. Let me just, as we all know, the brain's a geography of improvised rhythms. These rhythms have been implicated in multiple processes. Here's some work that we did some years ago using magnetoencephalography with the same kind of experiments. And really what I want to just point out that as you change the parameter, you can see over the noses up here, these are the sensors. They're called SQUIDs, superconducting quantum interference devices, that pick up magnetic fields that are generated by electrical currents in the brain. You can see that these transitions are also present in the brain. So here you have phase transitions as a collective effect in a very, very complex system. And in fact, even in earlier work with a fewer number of SQUIDs actually located over one hemisphere. Just draw your attention here. The black dots, I believe, are the behavior. So these dashed lines are where the parameter changes. So here we start here in a particular coordinated state. Every time you see number 2 come up, we make the system go a little bit faster, number 3 a little bit faster. So every time you see these hash marks, the parameters changing, and one of these is the brain, and one of these is the behavior. Yeah? So, and it's more than that, because notice every time you change the parameter here, it kind of perturbs the system, kicks it away from its steady state, and it takes time for it to relax back to where it was, and it doesn't go back to exactly where it was. And then the next time you change the parameter, you're getting closer to this instability, this transition. The next time you change the parameter, there's a bigger effect on the dynamics. The perturbation, the same perturbation has a greater effect. And what you see here is that it takes longer and longer to relax back to the initially prepared pattern before the system kicks, switches. And these are predicted properties of non-equilibrium phase transitions. Critical slowing down is the slower relaxation rate as you get close to the instability. Enhancement of fluctuations is another candidate landmark feature of these phase transitions. So you're seeing phase transitions in short, in movement, in the brain, I don't know if I have really time to do this, but you might say, well, this model you've shown, this coordination dynamics, works very nicely if you've got two interacting components. The person who has developed this for many components is a man called Kuramoto, and his work actually was, his work actually was extended by the late Art Winfrey. Any of you who have read the book Sync by Steve Strogatz, this is Steve Strogatz, will realize that it's basically about Kuramoto's work. And actually, Kuramoto was in Stuttgart 3 weeks before I was there. So it's very, very interesting. It's a very interesting scientific aspect. Now, I can't tell you much about these experiments at all, but our experiments involve 8 people interacting in real time, okay? And what the dynamics are of that. And so the whole idea was, how do we connect Kuramoto's picture of synchronization in very large ensembles of components with the HKB picture, which is typically dyadic by and large. Only a couple of components, only a few components are interacting. And through these experiments, a lot of work. This is the Kuramoto has been used as the go-to model in all these neural network synchronization, connectivity, chemical oscillations, applause, I'll show that in a second, heart cells, fireflies, and so on. And then you have this other picture of sort of lower dimensional nonlinear dynamics. The picture on the left, by the way, is inspired by statistical mechanics. That is, the mechanical behavior of very large ensembles of components. And this, of course, is nonlinear dynamics. This is one of the famous examples here where you have incoherent behavior in a concert hall. And at a certain point, everybody starts clapping in rhythm. Yeah? And so this transition from incoherent to coherent behavior is a phase transition. So I know you don't have time to copy down these equations, but you see again, it's a relative phase kind of description, or it can be cast in a relative phase kind of transition. Here's this heterogeneity parameter, distribution of frequencies of the components, and here's just a single sign function. And this is the famous Kuramoto result, that at a critical value of coupling, you get this transition from incoherent to coherent behavior. And here's our old, extended HKB model. You can see, the only big difference here is delta omega is the same as this omega I, basically. The only big difference is the second order term here. And actually, that second order term is responsible for multi-stability and switching and all the rest of it. So the question is how to reconcile the two. And all I can tell you at this point, and this is really, we're about to send this paper off, but actually we've got a formulation that reconciles the very many of Kuromoto and the rather few of HKB into a single formalism. If you just look here, you can see, if you cast out that B term, that's equivalent to Kuromoto, okay? And if you go from n equals 2 to n equals infinity, for n equals 2, this is equivalent to the extended HKB. So this thing captures the many and the few. All right. Little fast on that. So last part here coming up. Why phase transitions? Simplest expression of spontaneous self-organization in natural systems. Can all agree on that. Expresses the collective coordinated behavior of large numbers of elements, including neurons. The diverse arrangements of these microscopic variables produce the same outcome. That's called degeneracy, if you like, or functional equivalence. Phase transitions are a basic switching mechanism, basic decision-making, as it were, under certain conditions. No switches inside. Yeah? And whether this picture is correct or not, what I would like to emphasize is that phase transitions offer both a method, that is, take the system to where it's about to change qualitatively. That method is used to identify what the order parameters are, what the collective states are, and as a mechanism. And I would want to say it's a mechanism. Let me get now to the last part of this and say, okay, if you've gone along with this argument that phase transitions are manifestations in matter, rather the organization of matter, how matter changes state, and the coordinated movements of people and even the human brain, then what about the mind? Where does the mind come in? Okay, so in the last 8 minutes, let's bring in the mind. Okay, and here's the way we're going to do it. A little introduction. This is a beautiful book, by the way. It's part of the Newton project in Cambridge. It's called Priest of Nature. But most people think of Newton as being concerned just with matter in motion. You know, that's all. But actually, Newton was most interested in many things, and one of them was self-motion. Yeah? So the power of life and will by which animals move their bodies with great and lasting force demonstrate that there has to be other undiscovered laws of motion. In his letter to Oldenburg in 1675. And then this little dig by Alexander Pope, you know, could he whose rules the rapid comet bind describe or fix one movement of his mind? Yeah? I've got you, Mr. Newton. But Newton was really into how to understand self-motion and tried all kinds of experiments on this. Okay, a bit about the self. This again goes back to Maxine, now in her late years. Spontaneous movement is the constitutive source of agency. So this is a claim of subjecthood, of selfhood, the dynamic core of our sense of ourselves as agents, subjects, selves. So this thing that we take for granted, this spontaneous movement behavior, is at the heart of us actually realizing who we are. Yeah? One always wants the simplest kind of experimental model system that might allow one to reveal one's intuitions. Yeah? And this is a very famous experiment by Caroline Rouvet-Collier. I put a little quote here. Movement forms the eye that moves before the eye that moves forms movement. So here's the baby. And the baby, if you put a mobile, I always want to say mobile, but mobile over its head, and it's, you know, comfortable, it's had its nappy changed and stuff, it'll look at the mobile and find it attractive. It's noises and sights, it moves around. But it'll eventually get bored, as it were, bored, or lose interest, or just get a little bit anxious. Carolyn Rove Collier did the remarkable little experiment. She tied a ribbon to the baby's toe. The ribbon's now attached it as a tether to the mobile, and found that the baby liked to do that, right? And she called this mobile conjugate reinforcement. So now we're back to the behavioral sciences in spades here. And many people have followed this up. And here's her results. The paper was initially published in 1969, I believe. Here's the basic result. You can all see it. There's a baseline period where the baby's not coupled to the tether or to the mobile. Then it increases by a factor of 4 when the baby's tethered to the mobile. Yeah, a baby likes moving that mobile, right? And so this is the idea here that here's the phases of the experiment. Phase 1, the baby's detached, then it's coupled, and then it's detached. And you see this here. After the baby's, it sort of saturates off at a certain point, and then the baby's detached again, and it collapses down. And there are notions of how this is done, and perhaps we will discuss them in more detail later. I had this kind of idea, look, and it wasn't quite right. Let's do something that actually wasn't measured. Neither the behavior actually was measured very much. It was sort of how many kicks the baby did. I mean, there was no football here. The baby wasn't kicking anything. The baby was just moving its leg up and down. And nor there was any measure of the coupling with the mobile, nor was the world itself observed. So it's, what I would say scientifically, it was an incomplete description of the experiment. What Niels Bohr would say, you better give me a full description of the phenomenon here. And the full description of the phenomenon requires that you see what the baby's doing, you see what the world is doing, and you see how the baby's coupled to the world, right? And so this was the basic idea. The basic idea is not quite right, but here's the general idea was, look, here are the hypothetical movements of the mobile and the baby, and there's no phase logging at all. They're not coupled at all. And then when the baby realizes, hey, this is me doing this, the baby's pre-linguistic, of course, 3 months old. I'm only meaning this in a kind of metaphorical way. But the sense of the baby, I'm causing this to happen. I'm making the world change. This is agency. This is the origin of agency. That's why I love it. And so once the baby gets it, then it is, coordinated nicely. If the foot of the baby and the mobile are nicely coordinated. Well, we can do much better. And my colleague, Armin Fuchs, and I modeled this basically without getting into the mathematical details, but there's quite a lot of good motivation for the descriptions, the mathematical descriptions here. So we considered the baby's leg as a nonlinear oscillator, and these are the parameters of the oscillator. We consider the mobile as just, a damped mass spring system. It's just a physical system, You knock it and it'll go, and then it'll dampen down. And then there's a coupling here between the driving force of the limb and the effect it has on the mobile. And that's this term. You can see that it's an amplification here, the y² term, coupled to a damping. So this is what we call an autocatalytic effect. You stimulate, the leg stimulates the mobile, makes it go. The mobile is attractive and causes the leg to go more. And it's this kind of autocatalytic phenomenon that drives the whole thing. And when you do that, when you calculate everything, and I published this, and actually Armin and I published the technical article in Biological Cybernetics. But here's the Rove data that I showed you earlier, and here's the model. See, model does it beautifully. So here we think is how the self gives rise to agency. So let me just finish now. I'm sorry that there are so many words here, but The laws that bind us here, these nonlinear laws, biological coordination, coordinated movement, brain coordination, social coordination. It's a self-organized process governed by nonlinear laws, call that coordination dynamics, written on non-mechanical, informationally relevant variables that actually span the typical things that we think are separate, like organism and environment. Not in this company, I suspect. The laws refer to the flow of coordination states produced by functional synergies or coordinative structures, these temporary assemblies that are function-specific. Multi-stability, phase transitions, and metastability, which I haven't talked very much about, but which I did 9 years ago, are prominent features of the coordination dynamics. And this sort of self-enhancing positive feedback mechanism works for the emergence of self or agency, and it falls out of an analysis of these experiments on human infants, which actually are seldom considered in the new science of consciousness, at least so far. The I, or self, rather than being a novel state of highly integrated information or matter, is seen to emerge as a phase transition, a eureka effect of the self-organizing coordination dynamics. And without getting too philosophical here, I just say, I like this quote by Jerry Edelman. At the bottom here, it says, there must be ways to put the mind back into nature that are concordant with how it got there in the first place. That's why I like the idea that self-organization gives rise to selfhood and agency and so on. And so the laws that bind us here reconcile, in my view, the animate and the inanimate. The work that I only sparsely covered, the many, the few, and the in-between. Key part of this talk today was to reconcile the spontaneous self-organizing aspect and the so-called directed or intentional aspect of these complex living systems. And the phase transitions, as I said earlier, provide both a method and a kind of transcendent mechanism for relating the organization of matter, movement, and mind. So that's me finished. Thank you very much indeed for your attention.